Something very, very sophisticated. Please, Grigory.
Okay, thank you. The topic of my talk is presented here, and it is one of several fields of research I'm taking part, and it seems to be quite far away from the things I'm doing here together with Nikolai, but I hope I'll be able to present it in such a way that it doesn't need some special knowledge. So, Neumann-Poincaré. What is Neumann-Poincaré operator? Those of you who taught mathematical physics, taught students for the course of mathematical physics, or who have been mathematics or physics students, there is such a topic in partial differential equations or mathematical physics course, potential theory. So it's quite a long way to solve and to study boundary value problem for the Laplace, for example, operator using integral operators. One of these integral operators, the double layer potential, is called Neumann-Poincaré operator because it was Carl Neumann and Henri Poincaré who invented this method some 140 years ago. Such operator is under study still now. People try to know more, to relax the smoothness conditions of the surface and so on. But what probably you remember for the double layer potential for the Laplace operator, that this double layer potential is a compact operator, and it is important property which is used to reduce it, to invent different solution methods and Fredholm properties. But I'm going to talk about a similar operator, but in elasticity. So 3D elasticity, the equation will appear in due course, and there is also a double layer potential, which is used to study the solutions of boundary value problems in three-dimensional elasticity. And there is a renewed interest, namely there are some problems in wave propagation in the so-called auxetics material, some strange material with strange properties, and it was proved that in elasticity, this Neumann-Poincaré operator is not a compact operator. It is an operator of order 0, or in other way, a singular integral operator with 3 points of the essential spectrum. So the question which turns out to be important for the study of this strange material is to find out what can one say about the eigenvalues converging to this point. And here is the study I performed. It was inspired by some of my friends in Japan who study such materials. And now I'm going to some more mathematical text. So what is a pseudodifferential operator? The pseudodifferential operator is an operator which acts in the following way. So we have a function u onto which the operator acts. We make the Fourier transform, then multiply by some function a of xi, which is called symbol, and then make the inverse Fourier transform. Here it's written in a more graphic way. So we make a Fourier transform function, multiply by the symbol, and then make the inverse Fourier transform. And such thing is called pseudodifferential operator. The symbol, what is the symbol? This function symbol is expanded into asymptotic serials in positively homogeneous functions of order k minus j in psi variable. So this is written. What does it mean? Positively homogeneous. It means that if we multiply psi by some positive factor, then the symbol itself attains the factor in this to this power. And k, so it's a sum. And k, so when j equals 0, so we have ak, it has homogeneity of order k, and it's called the principal symbol. And k is called the order. What is written here is the operator acting on functions in the Euclidean space, but by the decomposition of unity and growing together, it can be defined by for a manifold. Vector case. We are interested in the vector case, so when u is not a function but a vector function of size n, and in this case a, the symbol is n times n square matrix. Well, so part one, spectral theory for zero order pseudodifferential operators. You see, elliptic operators of positive order. We studied the spectral properties of elliptic operator of positive order. It is the classical topic, more than 100 years old. There is huge literature of eigenvalue distributions, eigenvalue properties, starting from Hermann Weyl, 1911. For operators of negative order, and a typical operator of negative order is the resolvent of elliptic resolvent. I think there is echo somewhere. Probably you should switch off sound. Okay.
Yeah.
Yeah, switch off.
Володя, твой микрофон включен.
Well, so for operators of negative order, it's not so much known beyond the elliptic case, but still there is a good theory about eigenvalue distributions, distribution of elliptic operator of negative order. But we are talking about operators of zero order, and it tends to be the most complicated case. Until very recently, this case, the spectral properties of operators of zero order were studied very, very little. The essential spectrum is known. So if we have the scalar valued case, then the essential spectrum, such boldface sigma, is the set of values of the principal symbol. In the matrix case, it was not known. So if we have a zero order pseudodifferential operator in space of n component vector functions, which is principally is self-adjoint. So the principal symbol, it is the matrix, it is the Hermitian matrix. Then the session spectrum is the set of eigenvalues of the principal symbol. They are denoted by mu j, and essential spectrum is the union over all x and psi over cotangent bundle of these eigenvalues. So it may be some intervals on the real line, or it can be some points if these eigenvalues are constant. So generally it's a union closed intervals, but in a special case, some of these intervals may degenerate to isolated points. And it will be the case of the operator which is of interest for Neumann-Poincaré. So it's A0, so it's a function, the function of homogeneity 0 in psi variable, and also we will use a number -1. It is the symbol of order -1. Others are not interesting. Well, what we are going to count. So we're going to study discrete spectrum. What we're going to count. Here's the picture. You see? So let this be the essential spectrum, and by stars I denote the eigenvalues. So we fix some point, this point, and there is another observation point, and we move this observation point, omega minus tau, to the tip of the essential spectrum. And we count how many eigenvalues, how many stars are between this point and this point. And when tau goes to 0, so when this observation point goes there, then the quantity of eigenvalues grows. So black stars become red stars. And we are interested in this quantity, and this quantity is denoted by n minus of A is the operator, omega is the point of the essential spectrum, and this is tau, which denotes the moving points. In a similar way, we have, when we have upper tip of the essential spectrum, so look here, so we have essential spectrum, this is the tip, the end point of the essential spectrum, and then we also have two observation points, one fixed, and this observation point moves to omega, and we count how many are there red points, red stars. When it moves, black stars become red, and this quantity is denoted by n plus of omega. So we're interested in estimating the asymptotics of these two quantities, these two counting functions, as tau goes to 0. So when this observation point approaches the end point of the essential spectrum, so n plus and minus are explained in this picture, and n without sign is simply the sum. So it calculates how many eigenvalues are there in a two-sided neighborhood of the point of the essential spectrum. So these are two quantities. The easiest case is then there is one single point in the essential spectrum. So if omega is a point of the essential spectrum, the only one, then A minus omega is a pseudodifferential operator of order -1, and therefore it is a compact operator, and for compact operator there are beautiful formulas by Bierman and Salamiak, and here is this formula I want to show what is there. So this formula, it says how it gives the asymptotics of the number of eigenvalues to this or that side of the point of the essential spectrum. So tau I explained there. D is the dimension of the manifold where it is, and kappa is the order, the minus order. So in our case, kappa equals -1. And The quantity is, there is the order, so it grows as tau goes to infinity, tau goes to 0. Then there are coefficients, and look here, the coefficient, how to calculate. One should take the symbol, the principal symbol of what is there, of order k, take positive or negative part of the symbol, and then calculate the trace of this quantity. So it is a matrix. One take positive and negative part of the matrix, take this positive and negative part to the power d over k, and then take the trace, the positive, so the positive or negative eigenvalues. The leading case which we are interested in is when d equals 2 and k equals 1, kappa equals 1. This will be the interesting case. So here one should calculate this trace of the matrix to the power 2. That's the important thing. Well, so this is the formula when there is only one point of the essential spectrum.
I'm sorry, one technical doubt. Here, key is the same as kappa.
Yes, yes, yes.
Okay, thank you.
Well, now the next case when the operator A is not compact, but it is polynomially compact. What does it mean, polynomially compact? We have a bounded operator, but there is some polynomial, so that the polynomial of this bounded operator is a compact operator. And so there are, in this case, the essential spectrum consists of several discrete points, L discrete points, and there may be eigenvalues convergent to each of these discrete points. And we want to find out the asymptotics or estimates of eigenvalues which converge to some single discrete point. So we must somehow separate these eigenvalues, and the method consists in the following. When we study the eigenvalues converging to the point omega s, so ps, we take ps, such a polynomial, it is the form of polynomials. All eigenvalues are all points of the essential spectrum taken to the power 2, with exception to this point. Then it turns out that the operator bs, so the polynomial of this operator, is such that the leading term in the eigenvalues of A approaching the point omega s is the same as all eigenvalues of Bs. So somehow we cut away all eigenvalues which converge to all not interesting points and find out the behavior of interesting points, the one we are studying, omega s. So the question is for a given operator A to calculate this operator Bs and then apply the formula of Bierman-Salamiak. The important case here, when n, the size of the matrix size of the problem equals 2 and the dimension equals 2, A0 is the principal symbol, A minus 1 is symbol of order minus 1, and now some terrible picture. So this is the formula. You do not need to read the terms here. So this formula gives the symbol of this P1 of A. I remind you that we take S equal 1, and we are interested in eigenvalues which converge to point omega 1. To do this, we need to calculate the polynomial, and there is a terrible formula for the dimension, for the size of the matrix 3 and dimension of the manifold 2. There are 24 terms here. 24 terms. It turns out that this picture is important for further calculations. What is present here? Here present the principal symbol, the symbol of order -1, and also some derivative of the principal symbol in x variable and xi variable. So 24 terms. Looks quite impossible. Now we go to the second part, to the Neumann-Poincaré operator, the double layer potential. And at some moment we return to the picture we had before. So what is the double layer potential for some elliptic operator? So let us have some elliptic equation. By phi, we denote the fundamental solution for this elliptic operator in the d-dimensional space. And nu y is the normal derivative at the point y. And in the classical potential theory, this is the operator. It's an integral operator. This is the kernel, and this is the double layer potential. Or there is a joint double layer potential. The difference is that we take the normal derivative not at the point y, but at the point x. So these two operators, they were invented, in fact, by Carl Neumann and Henri Poincaré, and they were used for the Laplace operator, for which this fundamental solution is known even before that. They used to reduce the boundary value problem to the integral equations, and integral equations were much easier to study. So here are some dates. So for the Laplacian, it was Carl Neumann in 87, Henri Poincaré in 97, and then these integral equations of potential theory, they were studied by Ivre Fredholm that long ago, and one should say that these papers by Fredholm were actually the basis of what we call now the functional analysis. So it was Fredholm who proposed to consider not a particular equation, but an operator in some space. It was continuous function before that. Well, the Laplacian, when the operator L is the Laplacian, it is, as I said, it is the topic of courses in partial differential equations for modern students, and it is known that for nice boundary, this K, this Neumann-Poincaré operator, and also it's a joint, it is a compact operator. In fact, it's a pseudodifferential operator of order -1, and the eigenvalue properties are known since rather long ago. But we are interested in the elasticity operator. So they are called Lamé or Navier-Lamé equations for homogeneous isotropic material. These equations have the following structure. So L is the operator. There are two constants which are called Lamé parameters, mu and lambda. They describe the properties of the elastic material, and the equation is the following. So here divergence mu gradient of u, and here we have gradient lambda plus mu divergence of u. U is the function which describes the displacement. So it is 3 by 3. It's a three-component vector function. So this is Navier-Lamé equation, so more or less 100 years old, probably even more. And this is the basic equation in homogeneous isotropic elasticity, which is used in on thousands of occasions in calculations. Now, the fundamental solution for this equation, I remind you that the fundamental solution is such a function that if you apply the operator to this function, you get a delta function. It's known also since long ago. It's called the Kelvin matrix. So this is the fundamental solution. And the formula for the fundamental solution, there are some terms which are diagonal. The first term is diagonal. And this form, this term, the second term, it contains off-diagonal terms. So, and also there is this normal derivative, which enters in the Neumann-Poincaré operator, normal derivative for the elasticity problem. This normal derivative is the following one. So it involves mu is the normal derivative. So the result depends on these parameters, lambda and mu. And finally, the Neumann-Poincaré operator, the operator which we are interested in, is this one. So one should take the Kelvin matrix phi at x minus 1, apply this normal derivative t, and integrate. This is the operator. And the spectral properties of this operator are the topic of the study. The bad thing is, and it was discovered not so long ago, that even if the boundary is smooth, this Neumann-Poincaré operator is not compact. The off-diagonal terms in the Kelvin matrix, they constitute non-compact operators. I remind you that for the Laplace operator, the Neumann-Poincaré operator is compact, but this is not compact. It's not compact. It is a pseudo-differential operator of order 0, and it's not long ago that some 30 years ago that the essential spectrum of this operator K was found. So you see there are some names related which led to final calculations. So the following, that this Neumann-Poincaré operator is a pseudo-differential operator on the boundary of the three-dimensional body, and the principal symbol, it has the following form. So the operator acts on the boundary. So it's a three-component vector function, but it acts on the two-dimensional surface. So one should calculate this kappa 0. It is the such combination of Lamé constants, and the principal symbol is the following. It has, so psi is the tangent vector to the boundary gamma, and one can calculate the eigenvalues. The eigenvalues are 0 and plus minus this k0. It's easy to calculate. So there are three constant eigenvalues, and this means that this operator is polynomially compact. The Neumann-Poincaré operator is polynomially compact, pseudo-differential operator. It has 3 points of the essential spectrum, and we are interested in eigenvalues which approach these points of the essential spectrum. So the polynomial p of t, which kills this symbol, is the following. So one should take this kappa 0, and the polynomial is the polynomial degree 3. So theorem, the first theorem, it is the easy part. It says that the eigenvalues lambda ns, so the point s, it shows to which point we are in, we approach, n is the numbering of the eigenvalues. So the eigenvalues converge to plus or minus omega s in such a way so the eigenvalue number n approaches as n to the power minus 2, and if we use the notations I applied to the I explain into my pictures, then the asymptotics of this n plus minus are some coefficients times tau to the power minus 1/2, with some coefficients about which one can say that they depend on the point, on the boundary, and on these coefficients, Lamé coefficients lambda and mu. So the question is, the hard part is to find the geometrical meaning of these coefficients, because it is important implications to see from which side do the eigenvalues approach the points of the essential spectrum, how fast, and probably are there cases when there are no eigenvalues on the one side of the essential spectrum, but there are eigenvalues on the other side. So it's a hard part. Previously, before I took this task, there was one and only case about these eigenvalues. One and only case. It's a very recent paper by Deng, Li, and Liu, which was published 19. And it says the following, that there are sequences of eigenvalues which approach the points of the essential spectrum. Do you remember? There are 3 points of the essential spectrum, so there are 3 series, and these are these series. So this is the series of eigenvalues which approach the point 0. This is how they behave themselves. So this is the series which approaches the point minus k0, kappa 0, and this is the sequence approaches k0. These are exact formulas, and it's was a rather hard work to calculate these eigenvalues, even in spherical sense, because the variable do not separate. Looking at these formulas for the sphere, well, one should also keep in mind that these eigenvalues, each of them has multiplicity j. So due to a lot of symmetries, the eigenvalues have higher and higher multiplicity. The interesting thing that in all 3 cases, the eigenvalues approach the points of the essential spectrum from above, and there is nothing which approach from below. There are some mechanical explanation for this, not quite convincing mechanical explanation. So this is what was known, and nothing was known about this eigenvalue after, except that 2019. So we investigate where these properties remain for a general surface. The main theorem, which was obtained by considering this theory of zero order differential operators, what was explained before, is the following. First, let chi and w be correspondingly the Euler characteristic and the Wilmer energy of gamma. I will explain what is Wilmer energy. It is so the Euler characteristic is the number of handles the surface has, and the Wilmer energy, it says how strong is this surface bended. So the more it is bended, the larger is this W. So formally it is integral over the surface of the square of the sum of two principal curvatures. So these two quantities, kappa and w, and this function n of omega s and tau, the distribution function for the eigenvalues. So it is the sum of eigenvalues which approach from above and from below. It is tau to the power minus 2, and there are some universal coefficients which depend only on the material, lambda and mu. A and B, they depend only on the material, and here it is the linear combination of the Euler characteristic and Willmer energy. So it immediately gives way to study the dependence of properties of eigenvalues on the surface. So N and B are universal coefficient. As a sequence, one can see that there are always infinitely many eigenvalues near each of the point omega s, because it is impossible that both these quantities are zero. Next part, there are asymptotic formulas for n plus and n minus, so separately the eigenvalues which approach from below and from above. Also there are some coefficients, and the coefficients are given by explicit terrible formulas. I not writing these formulas. The coefficient plus is always positive. So this means that there are always infinitely many eigenvalues which converge to the point of the essential spectrum from above. But if there exists a point where the surface is strictly concave, so both strictly concave, it's more or less clear what does it mean. It's opposite to be convex. Then the coefficient with minus sign is positive. So there are infinitely many eigenvalues of the Neumann-Poincaré operator which converge to this from below. There is some more interesting property that if the surface is strictly convex, then there are only finitely many eigenvalues which converge below the limit points. So if it is strictly concave, there are infinitely many converging from below. But if it's strictly convex, then there are only finitely many eigenvalues below each point. Well, if you so here again this formula, which is the basic point, the formula for the symbol of P1 of A, symbol of order -1. So the formula which was presented in the case of polynomially compact operators. So here I use some colors. You see there are some colors which are which are blue and red, blue and red, blue and red. So it turns out, it is a result of rather hard calculations, that only blue terms, they depend on the geometry of the surface. All other terms here do not depend on the geometry. Moreover, so each of these 24 terms, it contains only one factor, only one blue factor, which contains some geometrical information. All other terms, they depend only on the material, on lambda and mu. So the order of actions, how one arrives to this main theorem. So first, to express the Neumann-Poincaré operator in convenient coordinate system, study the principal and the sub-principal symbol of K, what is denoted here by A minus 1, A number minus 1. Study the derivatives of the principal symbol, analyze the formula for this PS, the formula which is in the previous slide, determine the dependence of the terms on the geometry, and then still, since the calculations are terrible, we introduce a model case which contains all information. So, just a few words about how all this calculated. So this is what is here. It is the formula found by Kupradze some 60 years ago, 40 years ago. It is the expression of the integral kernel of the Neumann-Poincaré operator. So x and y are the points on the boundary, and nu is the normal, pq are showing the number of the variables. So this is the formula. You don't need to look at this formula, but it was used. So this is the formula. So this k written as an integral operator. What we need to do, we need to express this k as a pseudodifferential operator, finding principal and sub-principal symbol, and then what is there to put into the terrible formula with 24 terms, the symbols. So this is given in fixed local coordinates. And this operator has singularity. At the diagonal when x equals y, the singularities are in off-diagonal terms when p is not equal to q. So we choose convenient coordinate system and then calculate the symbol. So how to calculate the symbol? There is general theory by Hermander, how to calculate the symbol of integral operator. One need to make the Fourier transform of the symbol in the variable x minus x0. And in calculation of the symbol, it found that, in fact, the leading or the -2 terms in the expression doesn't depend on gamma, and the second -1 order term depends linearly on the curvatures with universal coefficients. So we make the Fourier transform. Here is a lot of technicalities. As a result, we need, so we denote by m this symbol of -1 of this terrible formula, 24 terms. It is the principal symbol of the polynomial of the Neumann-Poincaré operator. It is the term which determines the eigenvalue asymptotics. And as I told, each term contains, each of these 24 terms contains only one term depending on the curvature. Therefore, the sum of these terms, when we add, also a linear function of principal curvatures. So the structure theorem, it says that the symbol of this m is this 24 terms operator for which we need to calculate the eigenvalues. Expressed in special coordinate system has the form. So this principal symbol is K1 with some one universal coefficient, matrix coefficient K2, another K1 and K2 are principal curvatures. And next thing is that we need to calculate the formula by Birman-Salamiak. But in this particular dimension, we need to calculate the square of this expression. I remarked when I explained the formula by Birman-Salamiak that there is power 2. So here the power 2, it will be a bilinear expression in this K1 and K2, and any bilinear expression of two functions is in fact will be the linear combination of the product K1 and K2. And this, when integrated, it gives the Euler characteristics. And the square of the sum of K1 and K2, and this gives the Wilmer energy. Well, the calculations of the coefficients matrix is terrible, but some properties can be found from two particular cases. So in one particular case, when it is a sphere, we use the formula of Deng-Li-Liu, and it shows that this, so for the sphere, the curvature equals -1, and then it follows from the data in the formula of Deng-Li-Liu that these matrices M1 and M2 are non-positive. And this gives us, so since we know the properties of this formula, we can calculate what happens with different values of K1 and K2, since these two matrices are universal, so they do not involve anything concerning geometry. So we separated geometry and material. Another case where something can be done is a cylinder. So when the body is a cylinder, in this case, one of the curvatures equals 0, and instead of 24 terms, we need to calculate only 14. Even here, to find the asymptotics of eigenvalues, probably impossible, because one needs explicitly eigenvalues of a 3 by 3 matrix depending on parameters, and then integrate. But in the convex case, here, fortunately, the coefficient is a rational expression. And this is the rather short explanation how the calculations are done. At some moment, I needed to use some system of symbolic manipulations on the computer. Well, that's all. There are two sources where you can see details. One of them, which concerns polynomially compact pseudodifferential operators, was published in 21 in the journal of St. Petersburg Mathematical Journal. It was published here, and the other paper is not yet published. There is a preprint, which is devoted to the elasticity calculations. It's on the archive. Well, I want to add that the interesting topic here is to start to study a similar problem for the non-homogeneous body. So the material of the body has different elasticity properties in different parts. And here, quite interesting theory of pseudodifferential operators arises. And I hope that at some moment in near future, there will be some results concerning eigenvalue properties for the non-homogeneous body. Well, thank you. Hello.
Thank you very much.
Hmm?
I have a question, please. Hello? Can you hear me?
I hear, but I'm not sure about others.
Yeah, me neither. I am Carlos Villegas Blas. Thanks for your very interesting talk, Professor Rozenblum.
Thank you for attention.
Yeah, I have a couple of questions, please.
Yes.
One of them is, how about perturbations of this problem? And then you see, because this is points in the stable, in the essential spectrum are stable under certain types of perturbations. Is it possible to say so for that case?
Yes, it is. So the properties remain stable as, for example, if you change the surface gamma, so you deform the body a little bit. But if you deform the body, you cannot change strongly the Euler characteristics, the number of holes in the body, but you can change the curvature a little bit. So if the body is still convex under your deformation, if the body is still convex under your deformation, then the results about distribution of eigenvalues, they are stable. But if, for example, you have a convex body, but you deform it so that there is a little bit concave piece, then the properties of the spectrum change.
I see. Yeah, thank you. And I have a second question, please. Maybe I missed this point, but is there a kind of physical interpretation of this Neumann-Poincaré map in elasticity?
Well, it's a long story. It's a long story. For some, say for the last 20 years, there are a lot of studies of properties of the so-called plasmonic resonance. It's a kind of resonance, some surface waves and so on, which arise in some materials with wrong sign of structural constant. And it became important since the people could produce such materials. So the material with wrong elasticity, sign of elasticity constant, and so on. And it turns out that the study of wave propagation for such materials can be reduced to the study of spectral properties of this Neumann-Poincaré operator. So it explains various resonance properties in such terrible materials, wave propagation, and so on.
Great. Thank you. Very interesting. Thanks a lot, Professor Rozenblum. It's a pleasure to say hello. Thank you.
Thank you very much. Thank you for your attention.
I have a question.
Yes.
I have a question.
Yeah.
In fact, you presented us asymptotic formulas for eigenvalues approaching your essential spectrum.
Yes.
In fact, it contains the leading term of asymptotic. Is it interesting to find, say, second term of asymptotic, or is this information not needed?
it's not needed in implications. It's part one of my answer. Part two of my answer is that it is possible to find, it is always possible to find the remainder estimate in these asymptotic formulas. Part two. Part three, that in purely convex case, it is possible to find the second term in the asymptotics.
But no sense to do this because it's
It's terrible.
not
It's
interesting
terrible
for this
work.
problem.
It's terrible work, and no one is interested.
Okay, okay. More question or comments?
I have a question.
Yes.
Hi, Professor Rozenblum. Thank you for your talk. I mean, this is an innocent question. What you call the conormal derivative is what is called the traction.
So there is a formula for this conormal derivative. In fact, you are quite correct. Quite correct. In elasticity theory, this derivative is called traction. Yes, it is.
Okay, it's quite surprising that the double layer potential is not compact.
Well, it is known. It is known for the last 40 years.
Yeah, and of course you cannot prove anything of existence using Fredholm theory.
It is possible to use the Fredholm theory because the operator is not compact, but there is Fredholm theory for operators which are not compact. So one can say that the operator is not compact, but it is elliptic.
So the result will be essential spectrum.
Yes, the result is the essential spectrum. So the operator fits into the theory of singular integral operator. You see, in elasticity, for example, single integral operators have been used since very long ago. So it turned out that this particular Neumann-Poincaré operator is a single integral operator. So one can use Fredholm theory for such single integral operator. I must note that long ago, when this potential theory for elasticity was in early stages, a lot of people, even some serious people, they believed that the Neumann-Poincaré operator in elasticity is compact. And it was the Georgian school of elasticity who, by Kupradze, Mushilishvili, and so on, the people who found out that in fact it is not compact. So it's a long story of mistakes.
Okay, okay, very, very interesting. Any more question or suggestion or comment?
Questions, Kule. Are there similar results for the elastic shells?
I'm not sure that it works. You see, there is a different dimension for elastic shell. Probably something can be done, but I didn't go into this direction.
Okay, thank you.
So here, you see,
Volodya, it's your task to do.
you see here in this particular case, in three-dimensional Neumann-Poincaré, there is one very, very lucky circumstance, which is not present in other dimensions, and so on. It is that in the formula, in the Biermann-Salamiak formula for the eigenvalue asymptotics, these eigenvalues are to the power 2, exactly to the power 2. And this enabled one to use a lot of simplifications. I made the remark, probably even twice, that it is very lucky that it is power 2 which stands there.
Yeah. Yes. Okay. If no more comments on questions, let me thank our speaker again for a very interesting talk. And you know, you're always welcome to give talks in our seminars.
Oh, thank you. Thank you. So
And-
I will.
And our next speaker, yes,
I will send
You
you my slides, and here are the references.
yes,
That's a good idea. Thank you, Professor.
Yes.
I was about to ask you about the slides.
Yes.
So if you send it, I will appreciate it. Thank you.
yes. The best way to send it to Igor, say, or to me,
Yes.
and then we distribute to our list. Rafael, are you still here?
Yes, I'm here.
Yes, I am.
Yes, you are. Okay, so your talk is next. What is the title? What it will be about?
Let me check again what I said. Compact Toeplitz and Hankel operators on true polyanalytic Fock spaces.
Okay, it would be extended version of your Krakow talk.
Yes, that's true, but you don't have to have been there to understand my talk. It will be self-contained.
Okay, great, because not all of us were in
Yes, I know.
Krakow, so yes,
I know.
we are looking forward
Right.
to hear you. So
Good.
next, Wendy, is yours.
Yes.
Okay, great. So bye-bye to all of you. Take care.
Bye.
And no coronavirus to anyone.
Yeah.
Okay. Bye. Thank you.
Thank you.
Have a nice